Well, welcome to our next session. This time what we're planning on doing is starting Unit 2. And as you can see from your outline, Unit 2 deals with the solar system. And so we're going to talk about exactly what is in our solar system, how that solar system came to be, and the possibilities of other solar systems out there. But what I want to do to kind of start with is to back all the way up. And so I'm going to get up here, and I want you to pay attention to the galaxy that I have behind me. So think about this as a you are here kind of map. And so we certainly have this big, beautiful spiral galaxy. And we're going to basically go into the galaxy's arm, and we're going to look at a star that looks something like that little bitty star right there. And that's basically our sun, or a good representation of our sun. And so from that, then, we're going to come back and start talking about the neighborhood or the planets then that are around our sun. So let's go ahead and start looking at the PowerPoint. And so I want you to think of our solar system as basically our neighborhood. It's a town that you live in. Only in this case, that town contains about 8 planets. Not 9, guys. Remember, there's only 8 planets here. And we're going to then go ahead and talk about each one of those planets individually, as well as the moons that are around those planets, and look at the general characteristics. But we need to start with what's going on in the center, and that's the sun. Now, if we look at our sun as that main component right in the center of our solar system, then we know we have the sun as terms of an inventory. We have the terrestrial planets. Terrestrial planets means that we have a solid surface to walk on for those planets. We have gas giants, gas thinking the fact that we don't have that solid surface. Then we have all kinds of moons out there. We have asteroids, meteorites out there. We have comets. And then we have all this other leftover stuff that we're going to need to talk about. Exactly what does that leftover stuff tell us? Because it's extremely important. But now let's look at the mass percentage when we look at the solar system. And as you probably know already, the sun is going to have the greatest percentage of the mass. It's about 99.8% of the mass of the solar system. So granted, that's almost 100%, but it's not completely. So if we look at the sun, and then Jupiter being our largest planet is about 0.1%. All the comets, now notice guys, it's the comets, not the other planets. The comets have about 0.05%. All the other planets get together, and they have a mass of about 0.04%. Then you've got satellite and rings, and you can kind of see the very, very small percentage you've got there. Asteroids and this cosmic dust, so that gas and dust is left over from the beginnings of the solar system. So most of that mass is indeed considered right in the sun. Okay? And the only other planet that counts as an individual one is Jupiter. Otherwise, everything gets lumped together. So I want to kind of think about a scale model of the solar system. Because, I mean, we look at where we are within our galaxy, but how does that galaxy compare to the solar system? Hopefully all of you realize a galaxy is much, much, much larger than a solar system. Since that galaxy contains billions of stars, we're only centered around one star. So I want you to become the sun. And I don't care where you basically go stand, but I want you to stand someplace, and that's the center of our solar system. That's the sun. So I want to know, relative to where you are right now in your size, where are the planets? I want to know where the nearest star is, and where our nearest galaxy in terms of a large galaxy. Now, we know there are other smaller galaxies between us and Andromeda and satellite galaxies that go around our galaxy. But Andromeda is certainly the largest galaxy within our local group. So I want to know where that galaxy is relative to where you are as the sun. Now, we have 8 planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. So those are the order of the planets coming out. Well, if you would walk about 0.4 miles out and become the size of a pea, then that's looking at Mercury. So think what a nice little green pea is in terms of that size, and that's the planet Mercury. And Mercury is certainly one of the terrestrial planets. It does have a solid surface. Okay, about 0.7 miles out, and now it kind of looks like a small grape, that's going to be the planet Venus. And Venus is a lot of times called our sister planet, because at one time it was kind of assumed to be an awful lot like we are. We now know that completely is incorrect. But we'll talk about why that was originally thought of that way. So 0.7 miles out from where you originally started, we've got Venus. And then come on out about a mile, so a little bit further out from Venus, and we get the Earth-Moon system. And notice that the Earth-Moon system is basically the size of a grape. Not a small grape, because a small grape was Venus. So the Earth is a little bit larger than what Venus is. And now we're going to come all the way out to about 1.5 miles, and think of a small little bean, like a kidney bean. Okay, and so we've got Mars, and then come on out to about 2.8 miles, and we're going to have the asteroid belt. It's going to take 5.2 miles from where you started to locate Jupiter. And Jupiter is going to be the size of a very large grapefruit. So think about what a large grapefruit looks like and put it about 5.2 miles away from you from where you started. Then go 9.5 miles from where you started and make it a small grapefruit, and that's Saturn. And then we're going to take a huge jump. We're going to go from 9.5 miles out to about 20 miles. 19.5 miles to be precise, and that's where Uranus is, and Uranus is the same size as what a lemon is. And then we go 30.1 miles out, and we're going to get Neptune, and Neptune is also about the same size as a lemon. So that gives you kind of an idea within our solar system exactly what the distances are. So if I think about what the Earth is in terms of one astronomical unit, remember, one astronomical unit is about 93 million miles. That's the average distance from the Earth to the Sun. Then Neptune is about 30 AUs out. So go 30 times further out, and I'm going to get to the edge of the solar system as far as the planets are concerned. But please don't think that the solar system's edge is at that point. We know that it's much further out. Now, anything beyond Neptune is what we call beyond then our planets, but still part of our solar system. Now, if I want to think about the nearest star, which is Alpha Centauri, then I would have to go all the way to the moon. Wherever you started, the distance between you and the moon is how far that nearest star would be. And unfortunately, that nearest star is visible from the southern hemisphere, not the northern, so we can't see it. And then if I wanted to go ahead and see how far the Andromeda Galaxy is, then the Andromeda Galaxy would basically be relative to where you were as that center in the sun would be on the other side of our galaxy. So you can see what we're talking about when we're talking about distances to galaxies and even distances to stars relative to the distance between the planets within our solar system. Okay? So our solar system really is our neighborhood, the houses that you live around, or in this case, the planets that surround the Earth itself. Now, what I want to do to let you get a feel for distances not only within the solar system, but all the way to the edge of the known universe, and then go all the way into the atom and into the material that makes up an atom, which we call quarks, I would like for you to watch Powers of 10. Now, what you're going to start with in Powers of 10 is you're going to start with a couple that's basically in a park, someplace in the United States. And then we're going to start moving outward until we get to the edge of the universe. And then we're going to come all the way back in, go into the man's hand, and go all the way down to the level of the quarks. And so it'll give you kind of a feel for very, very, very large things in the universe compared to very small things. So let's take about 5 minutes and go ahead and watch Powers of 10. Okay, now that you've had a chance to go ahead and watch that, hopefully it gives you an appreciation for the vast scales that we have in our universe. And remember, right now we're not exactly sure where the edge of our universe is. So when we get to cosmology, we'll talk a little bit more about that. But what I want to do is kind of come back and look at the Earth, and I want to look at the planets as viewed from the Earth. So think about here. Now remember that the ancient astronomers knew about Mercury and Venus, certainly knew about the Earth. They knew about Mars, Jupiter, and Saturn. They did not know about Uranus and Neptune. Those things were not visible with the naked eye, so obviously the ancient astronomers, not having the ability to even have a telescope, were not able to go ahead and observe those. So we're going to look at the ones that were known and then go ahead and show you at least from photographs and what telescopes, when you look through the telescopes, look like for Uranus and Neptune. So here we've got Mercury and Venus. Got another picture of Venus there. And we've got Mars. Again, notice that you can see the red color of Mars. It will definitely be visible when you look at it. This is Jupiter. You can see a couple of the Galilean moons there on Jupiter. And there's Saturn. And then we've got Uranus and Neptune, which were not visible then, like I said, to the naked eye. We're looking at those through a telescope right now. Now what I want to do is I want to give you a feel for some of the planetary data as a way of introducing the various planets and their characteristics. And so the type of planetary data we're going to look at is distance from the sun, the period of revolution, which is basically how long it takes to go around the sun, and then the period of rotation, which we talk about rotating on an axis. We're going to look at the diameter, the density, and how the acceleration due to gravity compares on those planets relative to the Earth. And that's the same way with the density. With the diameter. We're going to look at that relative to the Earth. So let's go ahead and start with this table. And what I try to do is list all the planets and then give you a feel for those numbers. So if you can see across the top, I've got planets. There's the distance in terms of astronomical units. The period of revolution around an object, so you rotate around, or you revolve around an object. And notice those units tend to be days and then years. And the period of rotation, so you're rotating on your axis. Those are in days as well. And then you get down to the planets, some of the larger gas giants, we're looking at them in terms of hours. Then both the diameter and the gravity is given relative to the Earth. And then the density has units of grams per centimeter cubed. Okay? Well, if I look at Mercury, Venus, and the Earth, those all lie within 1 astronomical unit from the sun. So they're relatively close to the sun. Okay? You can see Mercury is about 0.38. You can see what Venus is a little bit further out, and you get Earth. Now, let's go out a little bit to Mars, about 1.5 times out further. And so those are the 4 terrestrial planets. And then you can see when we get to those gas giants, we've got Jupiter, Saturn, Uranus, and Neptune, that they are getting much further distances out. Now, those are gas giants, which means that there's no solid surface on there, and they're basically held together by gravitational attraction. We're going to find that they are much bigger. And in fact, if you go look at the diameters of those relative to the Earth, you can see that Jupiter, if we took Jupiter and we laid out Earths across its surface, would take about 11.2 Earths going across its surface. Okay, Saturn's just a little bit smaller, and you're going to go with about 9.4 Earths. And then you jump down to Uranus and Neptune. Remember, they were the size of those lemons. Well, they're about 4 times as large as what the Earth is. But within those terrestrial planets, the Earth is going to be the largest. Then Venus is just a tiny bit smaller than what we are. Then Mars is about half our size. And you can see Mercury is about 38% the size that we are. So Mercury is certainly the smallest planet in the solar system. Jupiter is the largest planet in the solar system. Now, if I look, though, at how long it takes to rotate on their axis, look at the numbers for Mercury and Venus. Okay, Mercury takes about 58.6 days to rotate once on its axis. Guys, how long does it take for us to rotate once on its axis? Well, 1 day. Okay. So now I look at Venus. Notice there's a negative in front of Venus, and there's a negative in front of Uranus. That's because Venus and Uranus are doing something kind of weird. And so we're going to have to talk about why they are behaving differently than all the rest of the planets within our solar system. Okay, and that has to do with things that possibly happened toward the beginnings when our solar system was forming. And so we'll come back to this a little bit later on when we talk about the formation of the solar system. So you can kind of see the rest of the numbers there. I'm not going to go ahead and read them to you, but at least you get a feel for this. And what I'd like for you to do is I will post this particular chart on Blackboard. So please go ahead and pull it off of Blackboard so that you can refer to that as we go ahead and talk about the planets. And then there'll be one like this for the moons of the planets as well. The other thing that I have posted on Blackboard is a nice general overview and kinds of questions that you need to be aware of as you go through the material within Unit 2. So please make sure you pull that off as well. But if I look at those, Jupiter, if I look at that largest planet of Jupiter, look that it rotates once on its axis about 9.8 hours. Now, Jupiter's 11 times larger than what the Earth is, and yet it's rotating much, much faster than what the Earth is. And so how come size then, the larger the planet, the smaller the rotational period? Okay, and so we'll come back to that as well when we start talking about the formation of the solar system. So in general, the further away from the sun you are in the solar system, the colder it's going to get. Each planet rotates on its axis and revolves around the sun. And in general, and I do mean in general, the direction of the rotation is the same as the direction of revolution around the sun. There are some differences, Venus and Uranus. We certainly notice this difference there. And so there are several planets that kind of have that different motion as compared to the norm. And we're going to find out Mercury's a little weird too, but we'll get to that point when we talk about the individual planets. Terrestrial planets have solid surfaces, and in general, they have smaller masses than the gas giants. Now, I want you to realize that we're looking at the observations today relative to terrestrial planets and gas giants. There's a good chance they may have been a little bit different in the past. So we'll have to look at the characteristics that we see in some of these terrestrial planets and talk about how they might have changed from when they were actually first formed. Okay? Terrestrial planets have larger densities than the gas giants. In fact, the Earth has the largest density of all the planets in the solar system. They tend to be composed primarily of rocks and metals. They show something called differentiation in composition due to the heating. So we know that these terrestrial planets have been heated enough that the heavier materials are going to sink to the bottom, which is why the core of these planets tend to be at the core, because they're made of metals, so they're going to be heavier, which is why they sank. And then the crust, which was lighter, would go ahead and float then to the top. So that differentiation in composition for the terrestrial planets is due to heating. So someplace during the time that that planet was formed, it underwent planet-wide heating to get that differentiation or that separation due to densities of the material. The crusts have all been modified at some time through geological activity, some of them more than others. Now the gas giants, on the other hand, certainly have larger mass than the terrestrials. They have no solid surface. They may be larger in mass, but they have a much smaller density. And in fact, if you go back and look at that table, you can see that if I had an ocean large enough, Saturn would actually go ahead and float. So it has a density less than that of water. It would have to be an extremely large ocean to float Saturn, but it could, hopefully someplace it could be done like that. Okay, so we also know that the gas giants are composed primarily of hydrogen with some helium and even smaller amounts of the other elements. Now, one of the things that we need to look at when we talk about the formation of our solar system is the fact that if I look out in the universe in general, the universe in general is made up of more hydrogen than it is anything else, some helium, and then even smaller amounts of everything else. So if we look at what the Earth is made out of, it's really kind of unique in the fact that it's not the same composition as the average or general composition within the rest of the universe. Well, that's because we are talking about the planets. We're going to find out that those stars are made of mostly hydrogen and helium, a very small amount of everything else. But because of the way it formed, these planets are made out of a little bit heavier materials. And for our definition, heavier basically means anything that is greater or heavier than helium. So we have hydrogen and helium. And then I know for those of you that have had chemistry, Your heavier elements tend to be the ones that tend to be toward the lower part of the periodic table. But basically for us, anything heavier than helium is going to be considered a heavy element. All of the gas giants do have ring systems. And that was something that was very surprising, and we didn't learn until we actually got out and visited Jupiter, Uranus, and Neptune. That they had a ring system exactly like what Saturn is. However, Saturn's is much, much larger, and Saturn's ring system are certainly visible from the Earth. In fact, if you go back and look at some of the original drawings that Galileo made of Saturn, he didn't recognize that it was actually a ring system. He thought that Saturn had handles on either side of it. And it's because he was seeing the ring system then on either side. And we know that Saturn's rings are basically composed of hundreds of individual rings that are made up of chunks of rock and ice, things like that. So when we talk about Saturn, we'll come back to that ring system because it is certainly one of the most beautiful things if you ever have a chance to look at it through a telescope, but it's also very unique. Is that rings of Saturn right now kind of a transient ring, and so we just happen to be looking at it at the right time, and given enough time, it will slowly go ahead and cease to exist as those rocks and ice chunks get pulled apart? We're not really sure. We also know the only planets that have ring systems are all the gas giants. How come gas giants get to have ring systems and terrestrial planets don't? All that goes back into what happened when we looked at the formation of the solar system. One of the things we'd like to be able to do is look at our solar system and compare it to solar systems that we find around other stars. And at one time that wasn't possible because we couldn't see those other solar systems. Now we know that those solar systems are pretty common, and we do have the ability then to go ahead and compare what we see out there with our solar system. And so we will certainly look at those comparisons. And then every one of the gas giants have numerous, and I mean lots and lots and lots of moons. Okay, if I look at the Earth, it only has one moon. Mars only has two. And yet if I look at Jupiter, Saturn, or Uranus, or Neptune, there's lots of them. So how come they have so many more? We don't. Now, the other thing about the gas giants is they do show differentiation in composition now due to gravitational effects, not heating effects. Okay, so these gas giants are very, very large, and so those gases then will go ahead and coalesce and be drawn together due to differences in densities, not due to differences then in heating. Now, one of the things we'd like to be able to do is to date the planetary surfaces. So number one, that assumes that we are talking about a solid surface. So we can't really date looking at Jupiter, Saturn, Uranus, and Neptune's surface. So we can only look at the terrestrial planets and date their surface. We're going to do that by counting craters and also measuring the radioactive decay that we have coming out of those terrestrial planets. And in doing that, we find out that the solar system appears to be about 4.5 billion years old. It's about the age of the sun. Now, if I compare that with the at least accepted age of the universe right now, it's about 13.7 billion years. So we're kind of a young little solar system there. Okay, universe is about 13.7 billion years old. We think our solar system is about 4.5. So that makes us about a third generation star. And for us, that's probably good because that means there are more heavier elements that are going to be formed with each successive generation of stars, because we find that we find that those heavier elements are formed in the death throes of stars. So originally it started out with mostly hydrogen with some helium, and as the universe has aged, we build up more of that heavier elements. Well, so us being a third generation star, then we do have more of those heavier elements, which then gets distributed when we go ahead and form the planets. So it's a good thing for us, we're a third generation star. So guys, that kind of gives you an introduction to what's going on within our solar system. And what I want to do for our next time is to go ahead and look at the Earth, because we're going to compare every other planet within the solar system to what we know about the Earth. So with that, I'll plan on talking to you the next time. Have a great day, guys.